Hi all, welcome back. So in today's video we are going to talk about how we are going to write a Verilog codes. As a beginner, even though you know about the concept, many of you suffer from how to write a code. Okay, how to write a basic code or how to develop the test bench for that particular code, how to pass the values into that particular design. Okay, so in this video we are going to talk about that. We are going to talk about how we are going to write a code in this Verilog. Okay, hope this video is helpful for you to many of the beginners because lately receiving many requests from the students that they are facing issues related to this particular thing, like how to write a basic code. Okay, so on this video we are going to talk about all of those things, right? So if you are new to this channel, consider subscribing this channel and hit on the notification bell also. Please share this to all the VLSI aspirants who also want to enter into design and verification domain, right? So first thing is half adder. So we'll be starting from basics. Basically, you all know that you will be writing in Verilog. You are having four coding styles in order to design your code. Like the first one is the basic one is switch level, and then the gate level, and then the data flow modeling, and then the behavioral modeling. Among this, behavioral level modeling is the highest level of abstraction, whereas the gate level is the lowest level of abstraction, and we don't consider the switch level. We have already discussed all about this. So in today's video we are going to see some codes, how we are going to write the code in gate level, behavioral level, and data flow modeling, right? So let us start from the combinational circuits. Okay, so in today's video we'll be seeing everything about combinational circuits, and in the next video we are going to see some sequential circuits like some flip-flops and all, right? So coming to combinational circuits, so let us see the first one, which is half adder. So when you are as a beginner and when you were asked to write a code for this half adder, how we are going to do this, right? So for any code, okay, either for when you want to write it in either gate level modeling or data flow or behavioral modeling, for these three things you need three different analysis, right? For the gate level, we also call it a structural level. So from the name itself you can say that based on the structure you will be writing the code. Okay, so from a half adder you will be designing the logic. Okay, so you know that for sum is a XOR b and carry is a dot b for the half adder. So for with these two logics you will be designing the structure. Structure is nothing but you will be forming the circuit based on the particular logic. So a and b means AND gate and a XOR b means XOR gate, right? You have designed this. Now when you want to write the code for this particular thing, first you need to know that in this structure a and b are inputs, sum and carry are outputs. So based on that you will be writing like module any name half adder is. Okay, there are two inputs which are a and b and output is sum and carry. Now if you see the logic here, what is the logic? One is XOR gate and one is AND gate. So one is XOR gate, one is AND gate. So since it is gate level modeling, you just need to give what type of gate it is. That's it. Okay, because these gates are already inbuilt with inside this particular Verilog HTL. That means they are gate primitives. They are already designed within it. So you just need to mention the gate type. Like this is XOR and this is AND. So XOR gate, and you need to name for that particular XOR gate as X1. Any name is fine, right? And then first you need to mention what is output and then the inputs. So if you see here, the first is output is sum and the inputs are A and B. So with that, the sum and A comma B. Similarly for AND gate also, like AND any name and then the carry which is output and then A and B which are inputs. N module. That's it. There is nothing more you need to do in this particular half adder logic. You just need to know the logic and then you just need to create the structure along for that particular equations, and then you need to write a code. Okay, now for this, if you want to write a test bench, that means if you want to pass the values, how we are going to do it? So for the same thing, have module half adder tb. So this is dut and this is tb, so I'm just naming it as tb, right? And then whatever that are given as inputs should be mentioned as rich, and whatever that are mentioned as outputs, those should be mentioned as wire. I have already explained why these are rich and why these are wire in my Verilog tutorials. I'll link the Verilog playlist where I have explained everything related to all the concepts that we are discussing, right? If you want to know that, you can check that playlist. I have mentioned everything clearly in that, right? So rich a comma b, since they are inputs, they are mentioned as rich and the outputs are mentioned as wire. Okay, you don't give inputs and outputs in the test bench, because test bench is only used to pass the values into that particular DUT. You don't need any inputs and outputs in the test bench, right? Right, as a beginner you should know that, because many of you will get confused them as input and output. No, you should not mention any inputs and outputs within your test bench, because test bench is nothing but it's an environment where you will be passing the values. Okay, passing the values to the DUT. You don't do anything related to input and output within your test bench, right? So now what you do after this, you will be instantiating the test bench to the DUT. That means you need to connect. How you are going to connect? This is the module instantiation. Okay, so this is my half adder S, which is my DUT. So I am connecting my half adder S to the half adder TB. So if you see here, this is my half adder S, UUB, and AB sum and carry. So these are AB sum and carry. So this A is connected to this B is connected to this sum is connected to this carry is connected to this. So you're connecting it with the module instantiation. So this is very important. If you are not mentioning this, then even though you pass the values, since there is no connection between the test bench and this DUT, you don't get the output, right? Because these values are not passed into the DUT. Right, so now coming to initial and begin. So you will be passing the values to A and B. Since A and B are rich, so they will be holding the values, and A is 0. So any type of values you can pass. Like I am passing to all the values, all the possible scenarios. Okay, so 0, 0, 0, 1, 1, 0, 1, 1. Okay, for every scenario I am giving some time, 10 time units of delay, so that you can see the output. Okay, when you are creating any monitor, dollar monitor or anything, you can see the output if you are giving some delays. Okay, it's if it's okay if you don't give delay also, that is also fine, but basically at least hash 1 unit delay is given means it is better. And then dollar finish. So since all the values are being passed, so I am giving this dollar finish and then end module. That's it. That is your TB. Okay, so in this way, try to write the code for both the combinational circuit and try to follow with it the test bench. Okay, so try to write it the DUT as well as test bench code, so that you will get to know, okay, what is happening, how we are going to write the DUT code and how we are RTL code. That means DUT is nothing but RTL code. How we are going to write the RTL code and how we are going to write the test bench. How we are going to pass the values through the test bench in that. Okay, so try to write them parallelly. As soon as you completed the RTL code, try to write the test bench for that, so that it will be easy for you to understand. Like you can analyze how you could pass the values, and if you want to check these values, what you need to do, like if you want to check the output, you need to give some dollar display or dollar monitor here. Okay, after dollar finish, or you can take another initial block and you can give like dollar monitor or dollar display in order to see what is happening, in order to get the output to be displayed on the screen. Why is it? Because if you are just copying and pasting this particular thing, and if you are seeing the output, you can't see the output, because since you didn't give any of the simulation tasks like dollar display or dollar monitor, since you didn't give any of them, you can't just see the output. Yes, the output is executed and your simulation is completed. You will get the notice that your simulation has completed successfully, but you can't see the output since you didn't give any of these functions like dollar display or dollar function, dollar monitor or dollar stop, anything, right? So this is the half adder code. Now for the same thing, if we are going to write the full adder, this is also same thing. Okay, since we are having the expression like sum is ax or bx or c in, and carry is a dot b dot c c dot in. So with this expression you are going to draw the structure, and with that structure you are going to write your code. Now the same thing here also, like if you see here, this is my half a full adder circuit. So sum is, if you see here, okay, these are by using the gates. Okay, now my second full adder circuit, I am using the data flow modeling, where the structure is not important but the expression is important. Okay, because in structural level modeling, like in gate level modeling, you need to know how many gates are there in order to write the logic, like what is the gate in order to write the logic. But in case of this expression, you just need to know the operators. Okay, what are the operators that belong to that particular XOR operator, like what is the XOR operator, because in data flow modeling, if you see, everything is based on operators. Expression, you will build the expression with the help of operators in case of data flow modeling. Now if you see here, even though they are expressions also, you know that A, B, C in are the inputs and sum and C out are the outputs. So A, B, C in are the input and sum and C out. Here there won't be any change in either of the three coding styles. Like in three level abstractions, input and output are just mentioned in that way only. There is no difference in the mentioning the inputs and outputs. Okay, the only difference occur in the logic. Like if you see, since this is the data flow modeling, you need to use the keyword assign. Okay, assign represents, it is the continuous data flow modeling. Okay, continuous way of modeling is nothing but, in data flow modeling you will be using the assign keyword in order to represent the continuous flow, right? Continuous statements, right? If you see here, assign sum equal to, so like if you see here, what is the logic? Sum equal to a xor b xor c in, carry equal to a dot b dot c in dot a. Now for the same thing here, a xor, so this is the xor operator. Okay, assign means you are assigning something. Okay, equal to, here basically this equal to is represented with assign. You can just remember it like that. Assign sum equal to a xor b xor c in. Similarly, assign carry equal to, what is it? A dot b, nothing but a and b. Okay, and then the plus is nothing but or operator. Okay, a and b or b and c in or c in and a, that's it. Okay, and then end module, such as simple as that. Now for this, if you are writing the test bench code, there won't be any change, because you need to remember that in either coding style you are writing, like in either of the level of abstraction, either it is structural level or behavioral level or the gate level, any level of abstraction, the test bench won't be changing. Okay, because through test bench you are passing the values, that's it. You are not doing anything in the test bench, you are not writing any logic within the test bench. You are going to test the logic that you have written in the RTL code with the help of this test bench code. So for either of these three levels of abstraction, the test bench is going to be same. Whatever you are going to write in the test bench, that is same for any level of abstraction. You need to remember that, right? So module, full adder, TB, and as I already told you, inputs are mentioned as reg, outputs are mentioned as wire, right? And then you made the connection, you made the instantiation for the DUT and your TB, right? And then you're going to pass the values. Okay, since it is full adder, it is having three inputs, so three values. Now if you see here before, since it is half adder, it is having two inputs, so two. Okay, similarly for 3, that's it. There is no change in this. If you see here, within initial and begin, within initial and begin. Okay, you are just passing the values. But here, since there are only two inputs, four combinations are provided. Since it is three inputs, so you can have 2 power 3, which are 8 combinations. So I am just passing all the 8 combinations, and then the, as usual, like dollar finish and end. If you want, you can also mention dollar monitor here, right? So this is how you are going to write the Verilog code in data flow modeling. So in gate level modeling, you need to know how to write a code with gates. Okay, like in gates, what is the thing that you need to remember? For any gate, you can just call the gate, and you can just name it, and you should first give the output and then inputs, okay, for connections. Okay, right? And then in data flow modeling, you just need to use the keyword assign. Okay, and then the operators. You need to know different types of operators within Verilog, because operators is very important in data flow modeling in order to write the logic based on the expression that you are getting, right? So this is the full adder. Now this is the full adder. Now we are going to design a code of full adder using two half adders. Okay, so using two half adders, you are going to build a full adder. Now, how you are going to do it? Okay, basically, when you are just a beginner, you need to know how to easily write a code in a shortest format, because the shortest the code is, the more accurate and the more pleasable it will be. So that is why you should know how to make your code as short as possible. There are various ways in order to write a code, because when you enter into Google and when you type, for example, full adder using two half adders, you will have various types of codes in that. Okay, one is written in one way, one is written in another way. So among that, you need to know how you are able to analyze it and how you are making it as short as possible, right? For this, since this is the half adder using two full adders, so first what I am doing, I am just writing the code for my half adder. Okay, a b sum carry, so I am writing it in data flow modeling. So assign sum equal to ax or b, assign carry equal to a and b. This I think you understand about it, right? And this is just my half adder. But what I want full adder using two half adders. So now what I am doing, I am just using the module instantiation technique here. So what I am doing here, okay, after this code, after writing the half adder code, I am writing the full adder code. Okay, module full adder, which consists of ABC in as input, sum carry as outputs. And since it is the half, I am connecting two half adders, there will be some internal connections, is it or not? Because if you are just talking about full adder, then there won't be any internal connections that you need to represent. Okay, but when you are connecting two half adders, why is it? Because one half adder's output is given as input to second half adder, and then depending upon that input, you will get the output. So that is why the internal connections are important when you are taking two components as two important main components here. So that is why I am mentioning the internal connections also. Here any internal connections you should mention it as wire. So basically connection means you will give it as a wire, right? So any internal connections are given as wire here. Wire C1 and S are internal connections within this, right? And then if you see here, this is my half adder. Okay, so if you see here, I am doing the instantiation here. Half adder is the name of my half adder code, and I am instantiating with name ha0, and I am just connecting it. Okay, in order to know how I have done this, what is this module instantiation and all, you should know clearly about what is module instantiation. Okay, I have already made a video on that. Okay, you can go there and check it out. So in this way, I'm using the module instantiation of these two half adders. That means I'm creating copy of my half adder, and I'm just placing two half adders, two copies of that, by just replacing the connections. Okay, here for first half adder the connections are a, b, s and c. For the second half adder the connections are c and s, sum and c1. So I am just placing two copies with different connections. That is called module instantiation. Okay, then after this what I am doing, I am just connecting both of this with assign carry equal to c plus c1. Okay, that means this is the output of first half adder, this is the output of second half adder. So I am connecting both this in order to get the final carry, which is c plus c1, right? So this is how you will be doing the connection for half adder, right? If you see the structure, if you analyze the structure, the same thing that you are going to do it here. Okay, so that is why first you should know how to create the structure and expression, and based on the expression how we are going to write the structure, right? So this is how you are going to use the module instantiation technique within the half adder, within the full adder code, in order to design two half adders. Now the same thing goes for full adder also. Like if I am going to design, since here if you see, this is the full adder using two half adders. Now when I am taking 4-bit full adder, the same thing happens. Why is it? Because for the 4-bit full adder I am having 4 full adders. Okay, just if you see, for 4-bit full adder I am having, just for a full adder I am designing two half adders. Similarly for 4-bit full adder I need to copy 4 full adders. Now if you see the structure here, I am having 4 full adders. Okay, now what I am going to do, I am just going to write a code for one full adder. Now if you see here, this is my one full adder code. Okay, A, B, C in, sum, C out. Okay, so based on the structure I am writing the code. So here if you see, this is my adder. For this adder basically I am having, what is, this is my 4-bit full adder. Okay, for this I am having 3 inputs, A, B, C in, and A and B are of 4-bit wide, since it is 4-bit full adder. And since A, B are 4-bit wide, so sum will be 4-bit wide and C out is 1 bit. Why is it? Because the C out is given, one C out is given as input to the other scene. Now if you see here, this is the scene and this C1 is given as input to the another full adder. So that is why the C out is only 1 bit. Now if you see here, when you are going to write the code, since A and B are 4-bit wide, so 3 down to 0, but Cin is only single bit, so that is why it is input Cin. Okay, and output wire. Okay, you can just mention it as wire. So basically, since you are having internal connections here, so instead of mentioning every internal connection, you are just mentioning everything is wire. Okay, it's no there is no wrong in doing that, right? Output wire. So sum is 3 down to 0 wide, and then the C out is 1 bit wide. So this is my structure, and with that structure I have mentioned all the inputs and outputs. Now you know that I need to have 4 full adders, so I am just instantiating 4 full adders with 4 copies, FA1, FA2, FA3, FA4, and now I am mentioning the connections. So for FA, sorry, here FA0, FA1, FA2, FA3, basically those are FA1, FA2, FA3, FA4 if you consider. So this is my FA1. Okay, for this FA1, what are the inputs? A of 0, B of 0, and C in. Okay, now what is the output? Sum of 0, which is S of 0, and then C out, which is C of 1. So this is my output. Okay, so these are the things. Now for FA1, if you see, A of 1, B of 1, and C out of 1, which is C of 1, and then the S1, C2. Okay, so in this way I'll be just mentioning the inputs in different connections and then end module. Now what I am doing, after making the copy, I am going to write the basic full adder logic. So I'm just making one full adder and I'm copying 4 instantiations for that. So I need to write the basic full adder code. So if you see here, A, B, C in, some C out. Okay, so I am writing for this basic full adder. You know how to write a full adder logic, right? So that full adder logic. Here if you say, I am just using the gate level modeling. You can just write it in, like if you see here, you can just write in this way. Like sum equal to A XOR B XOR C in, A of B, B of C, C of A. In this way, depending upon the inputs, names that you have mentioned, you can just write it like that, and then end module. Now the same thing occurs, either it is 8-bit or else it is how many bit adder. Okay, the only thing that you need to do is you need to increase this number and then make the connections based on the figure that you are checking out, right? In this way you are going to reduce your code by using this reusability and module instantiation techniques. You're going to reduce your code as much as possible, right? So this is how you're going to write your full adder. Now here if you see, 4 by 1 mux using 2 by 1 mux, the same thing. Okay, here since it is 4 by 1 mux, so I need three 2 by 1 mux, because only I need to use 2 by 1 mux. So that is why if you see, I need to see 3 2 by 1 mux. So you can either write this particular logic down, or you can either write this, because you may get it out. Like here I have made the full adder logic, and then I am writing the module second full adder. So you can just flip. You can just write the basic version of the full adder, and you can just write the 4-bit full adder down. Okay, because modules is, there is nothing that the this module is we only should write it in first and we should write it in second. There's no such thing. Okay, since they are all building blocks, you can just place anywhere you don't need, right? So this is my mux. Okay, so for the mux, if you see, I am having two inputs, one output and one selection. So based on that input, which is selection, is also taken as input, and two inputs I0, I1 and one output. So here I am just using the conditional operator. So what does the conditional operator do? If this particular selection is true, then first statement is executed. If false, then second statement is executed. That means if this selection is 1, then I1 is executed. If selection is 0, I0 is executed, right? So with that, I am just using a single logic. You can either use any of the logics you require. Okay, you can also use any operators like AND OR operators also to write this particular logic, but I think this is easiest for me, so I have written it in this way. But there is no rule that you should also write this 2 by 1 mux in this by using this particular logic only. Okay, since you are having the expression, you can use any kind of operator in order to write this 2 by 1 mux, right? So the same thing I am mentioning here, like this is my 2 by 1 mux. Now what I have done, I am taking my 4 by 1 mux. So since 4 by 1 mux, it is having two selection lines. Okay, so selection of 0, selection of 1, and then four inputs I0, I1, I2, I3, and then one output. Along with that, it is having some internal connections. If you see here, Y0 and Y1. Okay, and then with this, what I am doing, this is my mux to 1. I am making, since I am having 3 muxes, I am making 3 copies. 3 2 by 1 muxes, so 3 copies, and depending upon the connections it is having, like if you see here, I'll just explain one. Like if you see here, M1. So this is my M1, and this is my particular mux is this one. So what are the things it is having? Selection 1. Okay, SCL1. So since selection 1 is connected to both of this, so selection 1, and I2, I3 and Y1. Okay, depending on this, you are just making the connections, and you are going to complete your logic with this. Okay, for this, try to write the test bench. Here I didn't mention the test bench for any of this, because either it is 4-bit full adder, the test bench is going to be same. Okay, instead of here, since it is full adder, you are having 2 power 3 connections. Since it is 4-bit full adder, so based on that, you will be having the inputs. Okay, you can pass any number of inputs you require. It's not mandatory that you should pass all the inputs also. Okay, depending upon your way of writing, you can pass any number of inputs you need, right? So this is all for this mux. Also the same thing, you are passing the values, how many. For example, if this is 4 by 1 mux, based on the size you are taking, so you can pass the values, right? So this is my encoder. Now if you see the encoder here, okay, this is my logical expression. Based on this expression, I am going to write the logic. Now if you see here, for this, what are the inputs and what are the outputs, you need to see that. Now if you see here, I'm having 8 inputs and 3 outputs. Okay, instead of mentioning all the 8 inputs with different individual names, here I have reduced it so much short. Like what I have given, I have taken a vector representation for the input. Okay, now only a single name, which is D, and it is having 8 bits. So D of 0, D of 1, D of 2, D of 3, D of 4, D of 5, D of 6, D of 7. Right, in this way you are going to reduce. So instead of taking all the names D1, D2, D3, D4, D5, instead of taking all this, I have just reduced it to single D with vector representation. The same thing goes for Y also. Okay, now if you see, just everything is same. Assign Y to equal to what you will do, D of 4 plus. Plus means nothing but or. Okay, the same thing, D of 4 or D of 5 or D of 6 or D of 7. Okay, simple. Three expressions. Okay, three logics, right? And modules, such as simple as that. Now since you are passing the values, again the same thing. For passing values also, you have just made the module instantiation, and then if you see here, here also you can reduce it like this. Like first the D is 1. Okay, D is 8 tick. So the size of D is 8 bit. Okay, and the binary value 8 bit, and it is first value is 1. Now for every hash 1, now for every one time unit of delay, the value will be changing. I have written the for loop in order to make the value from 1 to 8. Instead of giving all the values like this, if you see here, you can just pass the values in this way. Like in the first, you will be passing as D of 0 equal to D of 1 equal to. Instead of passing all these values in this manner, what you can do, you can just write a for loop. Okay, so that it will be looping inside it, and you can just write the logic. You can here, if you see here, I'm just giving the display, so that, so for every loop, for every one time unit, it will enter into the loop, and the loop will be rotating until this I is less than 8, and then again it will be displaying, and then again it will be shifting. Okay, why it will be shifting? So basically, if you see the logic here, everything is shifting. Now if you see here, everything is right shift, so one has entered here, and then one. So for all the ones are with 1 unit of time shift, so that is what I'm giving, 1 unit of right shift. Okay, and then after one time unit, again it will enter, again display, again 1 unit, again enter. So instead of giving all these things, what I have done, I have just given it in 2 lines by using the for loop. Okay, right? So this is how you can reduce the logic in test bench also. Okay, instead of giving all the values in a blunt manner, try to make it as simple as possible. This comes when you practice. Okay, this practice of your practice in writing the for loop, your practice in writing the shift operators, your practice in knowing the shift operators, depending upon this experience of cut shorting your particular code will be existing. Okay, now since I have given you all these codes, try to write the code for this binary decoder. Okay, along with the test bench. Okay, and try to execute it. And if you get the output, please ping me in the comment box that you got the output, and also ping me any other examples that you like me to explain within this particular Verilog code series, right? So hope you like this video. If you like this video, please do like it and share to all the VLSI aspirants. That is all for today. Thank you.